All right. So welcome everyone to this seminar that is given today by Francis Wee. So Francis is a lecturer at ANU, the Australian National University. Prior to that, he was at UNSW. So all of us at UNSW deeply miss having him around, although he comes every now and then, which is great. So Francis did his PhD at UNSW, and then he moved to ANU to do a postdoc with Alan Welsh, and now he's still there. So Francis is mostly known for his work in statistical ecology, and today he's going to talk to us about spatial confounding in generalized estimating equations. So Francis, the screen is yours.
Okay, thanks, Boris. So thanks to, hopefully everybody can hear me and everybody can see the slides. I will attempt to try and semi-monitor chat as I go, but I'm certainly quite new to using Blackboard collaboration, so apologies about that. Okay, so thanks to Boris for giving me a chance to be able to present this talk today in front of, I guess you could sort of partly call it my home crowd. Yeah, thanks to sort of Boris for giving me a chance to present this as part of the UNSW Stats Seminar, as more broadly as part of the Stats Across Campuses initiative. So today I'm going to be talking about a project that I would probably call this project mathematically quite simple, but conceptually quite interesting and certainly quite challenging for me. It's a project that myself and a colleague of mine, Professor Howard Bondell from Uni of Melbourne, have been thinking about on and off now for actually over a year, and so we should really try to get to the end of it, I guess. And it's on this interesting topic of spatial confounding in generalized estimating equations. So how I'll structure this talk is that I'll sort of have a motivating simulation to start off with, and that'll then lead to, I guess, a review of sorts of generalized estimating equations. I'll then introduce the notion of spatial confounding and the idea of a restricted spatial working covariance matrix. Then I'll sort of compare this to, compare the pair, so compare the restricted spatial to sort of a standard or spatial, unrestricted spatial working covariance, then to restrict or not to restrict, and finally coming back to some simulations and hopefully a bit of time for discussion at the end. Okay, so I guess a bit of disclaimer to start off with. This is a brown bag seminar, and this, so the research is ongoing. Also, I did give a slightly shortened, a more raw version of this at the biometrics conference last year, when I guess in the not so distant past when conferences could be held in person. And so apologies in advance if there's some overlap with that, and if you heard that one before. And also some parts of this, depending on sort of how strongly you sort of feel about GEs in one way or another, some parts of this may be controversial. So apologies in advance if that's the case. Oh, I should also say I'll be sipping my tea along the way, so if there's some periods of silence, also apologies in advance about that. Okay. So I'm going to start off with what I would probably call a simple but motivating simulation. So I'm going to be dealing with count data. I'm going to simulate some count data or spatial count data. So the count data is from spatial. So I've got spatial locations in the unit square, and I'm generating them from a marginal Poisson model. So it's this count data, and this marginal Poisson model consists of a marginal mean, which has got a log link, intercept at a value of 1. And I've got one covariate which actually has a slope of 0, so actually doesn't have any effect. But it is a spatially structured covariate. So that covariate, that n vector of that covariate is basically, say, from a Gaussian process, and that means 0. And so this is, for example, a Matern covariance. Along with the marginal mean, I've also got a marginal covariance, which I'm going to denote as VSP. And it's spatial in the sense that I've got some spatial covariance. So again, this could be Matern, for example, Matern covariance. It doesn't really matter what it is, to be honest. It's kind of just Matern for now, plus some nugget effect, sigma squared E times the identity matrix. And then based on the marginal mean, marginal covariance, I've got this marginal Poisson model, and from that I simulate 1,000 data sets. Then for each data set, I'm going to fit generalized estimating equations, or GEs. I'm going to have 3 choices of the working correlation matrix. I'm not going to reveal what those are at this point. It'll actually become clear as the talk progresses what those choices are. But basically, I run the simulation, and these are the results that I get. So I've actually done it for 4 different sample sizes you can see up the top here. And what I've plotted here is essentially box plots of the estimated slope, remembering that the true slope is actually equal to 0. So I've actually got the true slope here. And each color represents a choice of the working correlation matrix, so the red, the green, and the blue. Okay, so based off these 3 choices, you sort of look at these results for a little while, and you probably look at it for a bit of while, and you probably think, well, let's move it along here. Nothing really to see here. It's kind of stock standard in terms of the results you would get. And the reason why I say this is that you look at sort of all 3 choices of the working correlation, and you can see that all 3 are approximately centered around 0. So you kind of see they're approximately unbiased. And also, as you increase the sample size, the variability of the box plots tends to 0. So that's indicating, at least empirically, there's sort of evidence of asymptotic consistency. But overall, sort of, and the other point is that of the 3 choices of the working correlation, you would probably pick the green one because the green one has the least variability, and also the variability tends to 0 the quickest, at least the empirical variability. So you probably would pick the green one if you could, because that suggests it's probably the most efficient in terms of the inference you would get. But overall, you would probably say that the results are kind of a stock standard and what you would expect. So let's move it along. However, what I'm going to do on the next slide, though, is actually take these results and present them in a slightly different manner. In particular, I'm essentially going to have a scatter plot, whereby on the y-axis, I'm still going to have the estimated slope as my y-coordinate. However, on the x-axis, I'm going to actually plot a quantity known as true alpha. Now, I'm not going to actually tell you what true alpha is at this point. It'll again become clear as the talk progresses what true alpha is. But it's just some data set dependent quantity that I'm going to have on the x-axis. And so if I actually plot these results, this is what I get. And so if you actually start to look at this sort of representation or visualization of the results, you start to think that maybe there's actually something more subtle and more deep that's going on here. First of all, you see that on the y-axis, in terms of the y-axis, you see that the red has the most variability, followed by the blue, followed by the green, and that's consistent with what we see up the top. What's more interesting, however, is actually that the dotted line here is the y equals x line. And what it seems to suggest is that actually the blue working correlation seems to produce pretty good estimates, or at least it's pretty closely correlated with this quantity known as true alpha. And so, whereas the red and the green seem to be doing their own thing. And so this seems to raise potentially a point about that, okay, well, at least to me, it kind of raises the initial question of, are the 3 types of GEs actually estimating the same thing? In particular, are the 3 choices of working correlation producing, are they always targeting the same set of estimates? And also, what is this quantity known as true alpha? So to try and understand, or to try and sort of attempt to understand and interpret what's actually going on with these results, we're going to essentially sort of do a review of sorts of generalized estimating equations. So GEs, very seminal work by Liang and Ziegler out in the late 80s. And sort of the main point about them is that we don't have distributions. We're just relying on, in this case, marginal moment assumptions. So suppose you've got a set of n spatially indexed observations. So SI is by spatial location, and then I've got a univariate response y, and then I've got a vector of covariance x. So with the G, I then set up a marginal mean, such as this, a marginal covariance, looks like this, and then some working correlation matrix R. And then based on this, I say, I guess, a GE, and so it looks like this quantity here. So 1 on phi is my nuisance or my scale parameter. D is equal to d mu d beta. A is that diagonal matrix of the variance functions, and I've got the working correlation, A minus a half, Y minus mu equals 0. And so I essentially solve this GE to get my estimates of the regression coefficients beta. Now, one of the main features of GEs, and indeed sort of one of the reasons that makes them quite popular, particularly in applied statistics, applied longitudinal data analysis, for example, is that they have this very nice property, which is that they're robust to misspecification of the working correlation. And what this essentially means is that, informally speaking, regardless of the choice of R, the coefficients in the GE always tend to the true values. They're asymptotically unbiased, they're asymptotically consistent for the same thing, and the choice of R really only affects efficiency. And from an applied point of view, at least for applied researchers, that's a very attractive property to have, because in some sense I mean, whether it's naively or not, it's actually led to a lot of applied researchers thinking, okay, well, I can sort of be a bit more relaxed about the choice of R because it doesn't affect it doesn't actually affect the point estimation in terms of the large sample properties. It's only affecting the efficiency of the inference and the estimation as well. But the coefficients always tend to the true values, are always targeting the same quantities, and so I can sort of rely on this robustness property to sort of get good estimates, so to speak. They're always targeting the same thing, and so you can choose R to be whatever you want it to be. So you can have it fairly structured, or you could go as simple as just choosing R to be an identity matrix in the simplest case possible. And so that's essentially one of the main features of GEs, and one of the reasons why they remain rather popular in applied statistics. Okay. So the next point regarding GEs is that GEs are often solved / thought of as iteratively minimizing a quadratic loss function. So if you set up this following loss function here and you iteratively minimize this thing, you'll you'll get estimates for the GE. So just to sort of explain that, you have 1 on 2 phi out the front, A minus a half Z, and where Z is this working response, minus A minus a half D beta transpose R inverse, and then the same thing again. And so the working response is evaluated at the current estimates B naught, and also A naught and D naught are also evaluated at the current estimates. And so again, conditional on phi and R, the only thing that's you're trying to solve for is beta, and you rock and roll with just solving this thing quite straightforwardly. Solving this quadratic loss function also turns out to be the same thing as if you just took the G and you did Newton-Raphson, you can show it's exactly the same thing as just solving this quadratic loss function. So this is just another way of, in a way, you can think of it as sort of rewriting the Newton-Raphson algorithm for the GE. Okay, so because we're in the context of spatial data, spatially indexed observations, we're going to have to choose a choice for the working correlation. I guess one choice, and a common choice for the working correlation in spatial GEs, is to set the working correlation to be a combination of some spatial correlation plus some nugget effect. So in this case, RSP is going to be equal to pi times sigma rho plus 1 minus pi times the identity, pi some weight between 0 and 1 that you typically estimate. Sigma rho is some spatial correlation. Again, it doesn't really matter what it is. For this talk, it could be exponential, could be Matern, could be Cauchy, could be squared exponential. It doesn't really matter. It's just some spatial correlation for now. Okay, so that's a very common choice if you're dealing with spatially indexed data and when you're fitting GEs. I'm going to do a very slight modification here just to try and simplify the notation a bit for the rest of this talk. And what that essentially amounts to is that I'm going to, rather than thinking about things in terms of correlations, I'm going to think about things in terms of covariances. So I'm going to combine my phi and my R together to form this thing called VSP, and I'm going to call VSP in the GE context an unrestricted spatial working covariance matrix. It's a bit of a mouthful, but that's essentially VSP. And I guess to be explicit about what that reparameterization is, I'm basically just letting sigma squared rho equals phi times pi and sigma squared E equal to phi times 1 minus pi. But essentially, it's just a reparameterization, and that's the resulting quadratic loss function that you get. Okay. All right. So GEs are often thought of in solving this, or / thought of as iteratively minimizing this quadratic loss function. you can actually push this a little bit further. And in fact, in the original Liang and Ziege paper, this was actually pushed further to actually think about the GE as more or less solving an iterative working linear model. So the GE really comes down to trying to solve this working linear model. A minus half Z, so the A minus half Z is my response here. And then I have A minus half dB, d beta, which is here. And then I have plus rho plus E. Now I've dropped the superscripts on naught just to simplify the notation again. But really, the key point about this is that this rho and this e's are essentially what we call induced effects. So the idea is that because you have this unrestricted spatial working covariance, which is of the form here, it essentially induces two effects. Yeah, this an induced spatial effect rho and an induced nugget effect E. So, and the key point about this rho and the E is that they're induced effects. They're not effects, unlike mixed models or random effects models, they're not effects that you explicitly assume as part of the model. They're effects that are induced by having an unrestricted spatial working covariance. So in particular, we don't have distributional assumptions on these things, again, because we're in the GE world. We only have moment assumptions. So we know that actually the expectation of both of these is 0. The covariance of rho is the spatial bit, and the covariance of E is the nugget bit. And so you can think about the GE with the unrestricted spatial working covariance as looking at this particular, or more or less being characterized by this working linear model here. Okay. So the question is, so what? What's so special about this? And in some sense, this review that I've done so far, really all of it is actually just adapting what is in the original Liang and Ziege paper. If you go back to the original Liang and Ziege papers on GE or the Ziege et al. Paper, this all of this machinery, so to speak, is coming straight out from that. I've just adapted it for spatial data. So what? What's exactly special about this? It turns out, however, that this working linear model here actually contains the ingredients of a phenomenon which is known as spatial confounding. Now, spatial confounding was really sort of brought into light or into mainstream spatial statistics by two papers here, Hodges and Rich in 2010 and Patsiorek in 2010. And since then, there's been a sort of a gradual building of research on the issue of spatial confounding, and to this day remains an active area of research and a somewhat contentious area of research as well. And so essentially what I'm saying is that this working linear model sort of contains the ingredients of this thing called spatial confounding. And so to understand what spatial confounding really means, what it comes down to, at least in the GE context, is that the spatial confounding comes down to basically rewriting the working linear model. So what we're going to do is we're going to let PD denote a projection matrix formed from D. And then what I'm doing is that I'm going to take this working linear model and I'm just going to add and subtract on the right-hand side. I'm going to add A minus a half PD rho, and then I subtract A minus a half PD rho. Then what I do is I basically factorize out the A minus a half D for the first two quantities to basically end up with this. And then what I'm going to do is I'm going to do a little bit more of a reparameterization so that I essentially end up with A minus a half Z equals A minus half D alpha plus rho bar plus E, where alpha is beta plus some additional quantity, and rho bar is, you could argue this to be a residual projected spatial effect, and it has this particular covariance here. But really the key point out of all of this is that if I now think about this working linear model, which is the same one as before, it's just, it's still the same working linear model as before, but if I sort of think about this version of the working linear model, and then I sort of reverse engineer and then back out into the GE world, what it seems to suggest is that if I now take a GE, but instead of using an unrestricted spatial working covariance, I now use something known as a restricted spatial working covariance, which is basically the covariance of rho bar plus some nugget effect, or the same nugget effect as before. It essentially suggests that my target's actually moved. So by changing my working covariance, or in effect the working correlation, I've shifted my target from being beta to being alpha. And at least for me, the first time I sort of played around with this stuff, I sort of found this to be a little bit of an interesting result, because At first glance, it seems to sort of, at least to me, a little bit sort of comes a little bit against sort of that notion I mentioned before about G's being robust to misspecification of the working correlation. That when you, regardless of the choice of the working correlation, you're always targeting, always estimating the same thing. Whereas this spatial confounding seems to suggest that maybe there's actually something more subtle going on, that actually if I change my working variance, I'm actually potentially changing my target. And so to sort of summarize where we're at so far with this, is basically I've got two choices of the working covariance matrix, the VSP, which is the unrestricted spatial, and the restricted spatial. And this effectively leads to two choices of the GE, the spatial GE and the restricted spatial GE. The spatial GE is pretty well established in the statistics literature since the mid-90s, early to mid-90s. There's been quite a bit of work on spatial GEs of this form. Restricted spatial Gs and the concept of spatial confounding overall, at least to our knowledge, hasn't really been that much talked about in the marginal model / GE context. Certainly for hierarchical and mixed models, particularly Bayesian spatial mixed models, there's been quite a bit of work, and more or less all the work on spatial confounding has more or less focused on the hierarchical and mixed model, particularly Bayesian spatial mixed model literature. But in the context of GEs, the concept of spatial confounding, at least from what we found, hasn't really been that much talked about. What I will mention, however, is that the idea that changing the working correlation changes your target in GEs has been considered before. So we're certainly not the first people to raise this point. There's been a work since the mid-90s and as recent as 2019 that has raised the notion, sort of more cautionary notes, that if you change the working correlation matrix in a GE, you are potentially changing your target. And most of this work has, again, focused on sort of independent cluster GEs and for longitudinal data. Whereas the idea of spatial confounding, at least from what we found, hasn't really been that much talked about in the GE context. Okay, so what I'm going to do at this point is I'm going to take a slight tangent in the sense that sort of this is what we're at. This is where we're at so far. And I'm going to take a very short tangent to talk about the special case of a constant mean variance. So what I'm saying here is that I'm going to look at GEs, I'm going to look at restricted spatial GEs and think about the case whereby I assume the variance is constant as a function of the mean. And mathematically, that basically means I'm going to set A to be, well, it's actually a scalar times the identity matrix, but effectively it's an identity matrix because I'm assuming the variance doesn't change with respect to the mean. Now in this situation, things simplify. So this I minus half PD becomes I minus PD, and the working linear model for the restricted spatial GE reduces down to this particular form here. And subsequently, the restricted spatial working covariance looks like this, has this particular form here. What's more interesting, however, is the fact that if I take this restricted spatial covariance matrix and take the inverse, that's basically what I can do. I just use the Woodbury identity and I'd get the inverse. And then what I do is if I now take this and then I substitute it back into the restricted spatial GE, it's pretty straightforward then to show that the restricted spatial GE simplifies to this particular GE form here. And this particular GE form is the same as what is known as the independent estimating equation. And the reason why it's called an independent estimating equation is that it's precisely the case whereby I assume the working covariance is a scalar times the identity matrix. So that's the IEE, independent estimating equation. It's kind of basically the simplest GE you can do. And so this is a rather interesting result because it essentially says that in this special case of constant mean variance, the restricted spatial GE will actually produce the same estimates as an independence case. And so to put it even more bluntly, the restricted spatial GE seems to produce, will produce the same estimates as actually if you ignore the spatial correlation altogether. And again, this is kind of a really, at least to me, seems a bit of a bizarre result. You can sort of do this restricted spatial GE, but actually you end up doing the same thing, at least getting the same estimates as just basically if you ignore the spatial correlation altogether. So that's essentially the result. Now, you can push this a little bit further, and in fact, if you just started deriving the sandwich covariance matrix and the sandwich standard errors, and I'll talk about sandwich standard errors a bit later on in this talk. Essentially, if you derive the sandwich standard errors, you can also show that they're actually the same. And so what this means is the fact that the restricted spatial GE produces not just the same estimates, but in fact the same inference, as if you actually ignored the spatial correlation altogether. At least if you use something like walled confidence intervals or walled hypothesis tests in the GEE. And so this is sort of and that's really all I'm going to talk about with regards to this special case. If you want to ask me a bit more about what the intuition behind this is, you can towards the end. I mean, I can attempt to try and give some intuition behind it. But that's really just a short tangent about that. In this special constant invariance case, you kind of get this really remarkable result. Of course, the constant invariance case is kind of a very special case in the sense that when people typically think about constant invariance, they're thinking about linear models or Gaussian data or normally distributed continuous data whereby you have an identity link and you assume the variance is constant as a function of the mean. Note, however, that in all this derivation, we don't require an identity link. So the only thing we assume is a constant invariance. We don't have to assume anything about the link function. The link function can be whatever you want it to be. And the reason why I raise this point is that it actually raises interesting possibilities about using variance stabilizing transforms. So you could potentially do something like apply a variance stabilizing transform and then apply an independence estimating equation. Possibly get at least approximately very similar results to as if you actually just use the restricted spatial GE. So that's just a bit of a short tangent, a semi-short tangent to this idea that the restricted spatial GE in the case of a constant mean variance function actually reduces down or simplifies to the independence estimating equation case. Okay. So I guess really the big question, however, is, at least to me, the big question at this point is what's actually going on, in the sense that we've got two choices of the working covariance, and this is estimating beta, this is estimating alpha. And so what we have to do is actually try to compare the pair and try to understand what those two, how to interpret those two effects. And so if I start off with the unrestricted spatial GE, this is the working linear model that we have, A minus a half Z equals A minus a half D beta plus D. Now, if I adopt the terminology of Hanks et al. 2015, and so Hanks et al. Is a paper in Environmetrics that has it's a very nice review paper on the issue of spatial confounding and basically Bayesian spatial mixed models. So it's a very nice review paper on that. And essentially, if I adopt their terminology, then you could call beta, they would probably call beta a conditional effect. And the reason why beta is a conditional effect, or why they call it a conditional effect, is that it's the effect of the covariates conditional on the effect induced by spatial working covariance matrix. So that is that by assuming a spatial working covariance, as in by using this working covariance form, you induce two effects rho and E, and the effect of beta is conditional on this induced spatial effect rho. That's logically why you would call it why we call it a conditional effect. We, however, prefer to call it an unpetition effect, and if it's not clear already, but it'll become clear very shortly why we call beta an unpetition effect. But essentially, it comes down to the fact that we don't petition rho. So we don't petition rho up, we don't divide rho up, and this induced spatial effect goes entirely into the second moment. In other words, it forms all of rho forms the working covariance matrix in the GE. Turning now to the restricted spatial GE, which has this particular working linear model form, Hanks et al. Would call this alpha an unconditional effect. And their interpretation of this unconditional effect is that it's the effect of the covariates after all variability in the direction of the covariates is pulled out of the spatial working covariance and into the mean. And so to try and give a little bit more interpretation behind this, we actually prefer to call alpha a petition effect. And the reason why we call it a petition effect is because it directly reflects the fact that we're petitioning rho up. So we're petitioning, sorry, there's sort of some construction work a little bit on my end, so apologies for that. Yeah, so essentially we call alpha a partition effect. And the reason why we call it a partition effect is that we partition the spatial effect rho into two bits, into two components. There's a component that's spanned by the column space of the covariates, and then there's the rest, which is on the orthogonal complement. And the idea behind alpha is that we take the first part, so the part that's spanned by the column space of the covariates, and we pull it into the mean, and we treat that as being a fixed effect. Whereas the remaining part, which is basically rho bar, which is that residual projected spatial effect, that remains random and forms part of the restricted spatial working covariance matrix. And that's essentially why we call alpha a partition effect. And it kind of makes sense, because if you sort of look at this additional quantity here, this is an ordinary least squares estimate. It's the projection of rho on D. And so that's precisely sort of what we're doing. We're taking that part of rho that can be explained by the covariates, or that is spanned by the column space of the covariates, and we're moving it into the marginal mean. And then the rest just remains part of the working variance. And again, that also sort of gives a little bit more background and context behind sort of arguing why what alpha is, because it is precisely after all variability in the direction of the covariates is poured out of the spatial working covariance and into the mean. Okay, so that's really sort of one way to think about what's happening with beta and alpha. We've got beta is a unpartitioned effect, whereas alpha is a partitioned effect. Now, another way to actually sort of approach this spatial confounding issue from another angle, essentially another way to think about it is in terms of multicollinearity. And when it comes down to what we're saying is that by choosing a working covariance, so in other words, by choosing that unrestricted spatial working covariance matrix, we're essentially creating artificial multicollinearity with the covariates. And so to sort of, again, sort of explain that a little bit more, by assuming an unrestricted spatial working covariance, we essentially induce this spatial effect, rho. So this is spatially structured. And the issue is that if D, which is basically the covariates, if D is also, or if the covariates are also spatially structured, then in finite samples, D and rho can be collinear. They can be correlated in finite samples. And so spatial confounding really comes down to multicollinearity. You have this multicollinearity that's occurring in D and rho. And so like we sort of teach, I guess like we teach undergraduate students in a standard regression course, anytime you have multicollinearity, you have to think about, one of the two big issues are the bias, your regression coefficients, an estimation of them becomes an issue because of bias, and also inference on those regression coefficients also becomes a bit of an issue, again, because of the collinearity that's in play. And so, in a way, spatial confounding really comes down to whether / how you want to try and partition that collinearity. In the unrestricted spatial GE, there's no partitioning that takes. You sort of just live with the multicollinearity, and then the beta is conditional on the rho that takes place. Oh, sorry, on the rho that is induced. In the restricted spatial GE, we partition and we quote unquote try to correct for that collinearity. And the way we correct for that is that we try to move the part of rho that can be explained by D into the mean, and then the rest remains, is orthogonal to that, and so it remains part of the working covariance. And so if you think about sort of things like partial regression plots and partial correlations, these are kinds of things in statistics that exist to try and are also sort of along the lines of trying to correct for collinearity and trying to sort of show the proper adjusted effect. And the restricted spatial G is sort of along those, you can sort of think about it as trying to sort of work along those lines, trying to sort of think about partitioning and trying to correct for that multicollinearity that's in play. And so again, to sort of sum up where we're at, we've got basically the unrestricted spatial GE, which estimates the unpartitioned effect of the covariates, and then the restricted spatial GE, which estimates the partition effect of the covariates. So this is beta, excuse me, and this is alpha. Okay, so then because you basically have two of play and we have interpretations of them, the natural question that arises is, okay, well, to restrict or not to restrict, you know, are we interested in beta or are we interested in alpha? Now, in the mixed model world, at least from what I can tell, there's no consensus on this. It depends on your question of interest. It depends on what you think the true model is, and much smarter people than me have thought about this problem. In the context of GEs, there's also no consensus on this, at least in mine, Howard's brain. What I will do, however, is that over the next couple of slides, I just want to give one possible reasoning as to why you maybe want to use restricted spatial G. It's kind of the new working covariance matrix that I'm introducing here. It's not a definitive argument, it's not conclusive, it's just one possible reason for why you want to use a restricted spatial GE. And this is kind of where things can get a little bit controversial. But essentially, the reasoning is quite simple. It really comes down to thinking about, okay, what is the main objective? What is the main aim of a GE? At least when you apply it in this context. Now, to me, the main aim of a GE, at least in this context, is to explain as much of the marginal mean as possible using covariance. That's the goal for the GE. You're trying to explain the marginal mean, and you're trying to use that, but use the covariance to try and do that. The working covariance should be residuals. The working covariance should not contain any information about how the spatial structure of the response can be explained by the covariance. And so if you sort of, excuse me, if you sort of buy into sort of these two reasonings, and if you sort of believe this is what the GE is trying to do, then the restricted spatial working covariance should be aims to fulfill this goal, because it aims to ensure that the marginal mean, or that everything that the covariance can explain about the marginal mean goes into the marginal mean. And that's kind of reflecting that, again, correcting for that multicollinearity. So if this is sort of your, if you're sort of going along this kind of reasoning, then the restricted spatial working covariance should be the thing you should try to use. So again, it's not definitive, it's not a conclusive argument. The restricted spatial G estimates the partition effect. This is the thing to do because it ensures everything that the covariance can explain about the response goes into the mean. There is, however, one downside to this, you could argue. Or you could call it a drawback. And the problem, well, it's not an issue. One of the issues is that this partition effect ends up being data set dependent. And this is not too surprising, because if you go all the way back to here, you can see that this alpha is now a function of the covariance and also a function of the induced spatial effect. So if you change your spatial locations and supposedly your covariance also changes as well, then alpha also changes. And what this essentially means is that your target, your estimates, not well. It's not only that your estimates change, but what your estimates are estimating also change. So your target actually changes with each data set. And so your target inference, your target quantity, is now also a data set dependent quantity. And this, you could argue, is a little bit of a drawback, because maybe the argument is that, well, the GE should actually be estimating unique population averaged effect. And if you want to estimate the unique population averaged effect, then you should be estimating beta, because beta, at least in general, doesn't change with data set, it doesn't change with the covariance, it doesn't change with the spatial locations, it's just that unique effect. And so if you sort of go with this reasoning, then you should be, by this reasoning, you should actually be estimating the unpartitioned effect, the unrestricted, and so therefore you should be using the unrestricted spatial GE. And so those are sort of two reasons, or sort of one reason for this side and one reason for this side. Again, I don't think there is a definitive answer, but I think there's sort of a fair arguments to make, or fair reasonings on one side or the other with regards to which GE or which working covariance you're estimating. Oh, sorry, end up choosing. Okay. So what I'm going to do on the next few slides, actually, well, I should say that basically this is pretty much all I wanted to talk about in terms of actually the working covariance and the interpretations of the two effects. What I want to do on the next few slides is talk a little bit about standard errors. And so in terms of standard error, GEs, probably the most common approach to trying to get standard errors, at least the most classic textbook approach, is to use sandwich covariance matrix. So for the unrestricted spatial G, for instance, you essentially form the sandwich matrix looks like this. So you have the bread matrix, you have the meat, and then you have the bread again, or the bread inverse. The only sort of, I guess, interesting or tricky bit is the V naught. V naught is basically the true marginal covariance of the response, And so in practice, you need to get some estimate of this. Again, I'm not really going to talk about how you estimate this. It's more that in practice, obviously, you need some estimate of this. But in general, this is kind of the classic sandwich covariance form that you get for the unrestricted spatial GE. In the restricted spatial GE, same deal. You still can form the sandwich covariance matrix. You can still get your standard errors doing that. So you have the bread again, you have the meat, and then you have the bread. The estimates from the restricted spatial GE, and the only bit is that you change from doing a VSP to a VRSP. And so based on these two things, you can rock and roll with your standard errors. And so really, it's just a usual sandwich, right? Question mark. It turns out, however, that once spatial confounding comes into play, the issue again becomes a bit more subtle. And to explain this, the first thing to point out is that when people deal with standard errors or doing inference in GEs, particularly with their standard errors, they're really a lot of discussion is around efficiency. And usually the talk of efficiency is about how good your guess of the true covariance is. The closer your working correlation is to the true, the smaller your standard errors. And that's exactly what you would expect. And that's basically very intuitive. And that's the usual discussion regarding efficiency. The issue, however, is a little bit more subtle once spatial confounding becomes involved, because as we seen before, your guess affects your target. And so essentially the lack of efficiency, if you end up having a lack of efficiency in your inference, then this actually also relates to choosing the wrong target. And what I mean by this is, essentially I'll give two examples. This one is, suppose in the first example, your target is the partition effect alpha. So you're trying to do inference on alpha. If you use restricted spatial GEs and the associated sandwich covariance matrix, then you are as efficient as you can be. And in fact, your sandwich reduces down to your model-based or the naive model-based standard error. But the main point is the fact that you're as efficient as you can be because the restricted spatial GE contains the working covariance that reflects the fact, the working covariance in the restricted spatial GE is actually trying to target alpha. So you're trying to do inference on alpha, your working covariance reflects the fact you're trying to do inference on alpha, and so you get efficient inference. On the other hand, suppose now your target is the unpartition effect beta. However, let's suppose you continue to use restricted spatial GEs and the associated sandwich standard errors. In this situation, you end up being less efficient. And the reason why you end up being less efficient is the GE doesn't reflect the target. That is, you're trying to do inference on beta, but the working covariance in here actually is trying to target alpha. And so in order to try and get valid inference on beta, you have to pay the price of wider standard errors, and so you're less efficient. And so these two examples are just to illustrate that this discussion of efficiency still is completely makes sense and is completely true, but the issue is just a little bit more subtle because of the fact that changing your working covariance changes the target you're trying to estimate. And so standard errors can be constructed, for example, the sandwich covariance, and efficiency is determined by how close your working covariance guess is, as well as actually whether it reflects your target or not. Okay, so I've got a little bit of time left, and I can actually now come back full circle to the simulation. So this is the last part of the talk. And I can come back full circle to the simulation that I showed you at the beginning. I can embellish it with a little bit more information. So it's still a Poisson model. The spatially structured covariance ended up being from an exponential spatial covariance. I can now actually say that the marginal covariance I used is of an unrestricted form of this form here, and the sigma, and this was actually also an exponential covariance. And the spatial scales in both cases were chosen to induce moderate spatial dependence. Most important point that I can now reveal, you could say, is that the three choices of the working correlation I have were the independence case, the unrestricted spatial, and the restricted spatial. And so these are the results that I showed you at the very beginning. The red is the independence, so you might not be able to read that, but basically that's independence, the red. the green is the unrestricted spatial GE, and the blue is the restricted spatial GE. And this is why now you can sort of look at these results, and you can see that this is why the blue, at least the estimates from the blue working correlation, lie approximately on the y equals x line, because the restricted spatial GE actually produces fairly good estimates of alpha. Whereas the independence case, the red one, and the unrestricted spatial GE, which is the green one, is sort of doing their own thing. In particular, the unrestricted spatial GE is actually producing estimates of beta. I can talk a little bit more, well, I can sort of show some additional results for doing inference on beta, the unconditional effect. So I've got these, I've constructed 95% walled intervals, and this is the coverage probability and the mean width. And for all cases of the working correlation or working covariance, they're basically more or less at a nominal level. But not surprisingly, the unrestricted spatial, which is the green one, has smaller standard errors and smaller walled intervals. And in light of what I discussed a few slides ago, that's not surprising because of the fact that in this case, by using the unrestricted spatial G, the working covariance there actually reflects the target you're trying to do inference on. And so you're getting efficient inference here. Whereas the independence and the restricted spatial, the working covariances there don't actually reflect the target you're trying to do inference on, and so you pay the price for having larger standard errors. You can do similar things with Gaussian data. So basically, you take the same simulation design, you simulate from spatially continuous data with from a Gaussian model. Very similar results to what I showed you before. The main difference is the fact that, well, the first part is the fact that the independence, or the IE, and the restricted spatial G produce the same estimates. So in fact, the blue and the red actually completely overlap each other. That's why you can actually only see the blue. So the independence and the restricted spatial G produce the same estimates. That's not too surprising given what I mentioned before about the constant mean variance case, that being a special situation whereby these two are equivalent. What's more interesting, well, I guess probably the more interesting point, at least empirically, is the fact that the blue and the red actually, the estimates from the blue and red actually line up on the y equals x line perfectly. So they actually end up estimating the true partition effect perfectly. And if you want to ask more about why that is later on, you certainly can. It basically relates to how you end up actually trying to construct the true alpha. But the main point is the fact that the independence and the restricted spatial produce the same estimates in this scenario. You can do the same thing with, you can go talk about inference on beta, and you get basically the same results, or very similar results, sorry, as in the Poisson case. So nominal coverage probability, all three choices of the working correlation plot, but you do pay the price of efficiency for the independence and the restricted spatial GE. You can do the same thing with spatial binomial responses, but the results are slightly less stable, unfortunately. And finally, you can also generate data from a model which contains where the true marginal covariance is actually a restricted marginal covariance. So it's of the form VRSP. And in that situation, the estimates from all three GEs are centered around the true partition effect, and the restricted spatial GE, in this situation, perhaps not surprisingly, ends up being the most efficient. So you can sort of do sort of the other kind of simulation, whereby you generate from a restricted marginal model. So you can do that as well, and the results are similar, what you would expect. Okay, so just to finish up a few more slides. Really, what I've talked about today with spatial confounding Gs is really just the tip of the iceberg, and there's a lot of things there's a lot of questions that get raised, and some of them I have answers to, some of them I don't have answers to. So how do you get a true alpha in the simulation? What is the independence case actually estimating? What about large sample? And what about connections to other fields like time series regression and endogeneity and panel data model? So there's a lot of food for thought in terms of trying to think about spatial confounding in Gs in general. Probably the thing I'll actually end on is I actually want to come back to this particular question here. So at the beginning of the talk, I mentioned that a very nice feature, or a very well-known feature of Gs, is that they're robust to misspecification of the working correlation. And so having sort of gone through this project and sort of having given this presentation, you can sort of re-ask the question, well, are spatial Gs robust to misspecification of the working correlation? And I guess having sort of now worked on this project, my answer to this would probably be, well, yes, but actually no, but actually yes. And essentially what I mean by this is that spatial Gs are robust to misspecification of the working correlation, but it's not just an efficiency issue. If you change the working covariance, you are potentially changing your target, because you're changing the target you're trying to do estimation and inference on, and that's because of the multicollinearity that comes into play. And so it's not just an efficiency issue. You have to think. I guess my main message is that I sort of really urge practitioners to be a little bit more careful. You can't be too cavalier with the choice of the working correlate. You have to think a little bit harder about the assumptions you're willing to make, and also the question, and also the target you're actually trying to do inference on, and estimation as well. And so I'll end off with this a very nice quote from Noel Cressy, which is basically, what is one person's spatial covariance, maybe another person's mean structure. And that kind of perfectly encapsulates the issue of spatial confounding, particularly in the context of GEs. So that's what to talk about. Thanks to everyone for listening, and I'm happy to, those are my contact details, and I'm happy to take any questions.
Thanks, Francis. That was great. So there's a round of applause for you from everyone, I'm sure. If anyone has any question, just please unmute yourself and ask the question. Or you can type it in. Pauline has a question. Pauline, we can't hear you, but
sorry, I was waiting for my turn. Thank you, Francis. This is a really interesting talk. It's really clever idea, I have to say. And I really like your quoting to Noel Cressy, because very often this is what happening, isn't it? In practice, that you can either decide to fit as random or fit as a fixed effect. That really depends on what tools and what goal you've got. I really like the way you presented your a box plot, then the scatter plot for what is true alpha is, that one, because this is really what Crowder paper in 95 says, although you didn't really give a very nice illustration, is saying, well, what is actually being estimated in GE in terms of their working correlation. And I think this particular plots really sums up for what he actually saying at the time. So that's fantastic. So this is my comment. Sorry, that's not my question. I do have a small question though. Is in regarding to your row in this case, what is the size of it? What's the dimension that you fit it in a normal data set? Can you give us an example? Just have an idea.
Sorry, the row?
Yes, the row.
Okay. Okay, so it's a good question. So, yeah, okay. So in this context, just because of the way sorry, let me try and go back to something that is workable here. Yeah, something like that. In this context, a row is, just because of the way the mathematics lines up, the row is effectively this is a vector with the dimension is the same dimension as the number of observations or number of spatial locations. So it is an n vector, and so it's kind of like a full spatial effect, and it's got this covariance, which is, you could argue it to be say a maternal, something that's spatially correlated. So it kind of reflects a spatial correlation. So it is sort of the same dimension as the number of observations. Hopefully that answers your question. The one thing I will say about this, which kind of, and I'll sort of go back to the simulations at the very end, about this is the fact that one of the interesting things about trying to simulate from the marginal model is that you don't have a row. So when you sort of, in sort of a lot of, well, if you're fitting something like spatial mixed models, then you explicitly set up the row. You sort of simulate the row, and then you condition on the row, you simulate the responses on that. In a marginal Poisson model, all you're doing is that you have a marginal mean and you have a marginal covariance, and then you just simulate the responses. And so one of the issues that we faced in the simulation was basically we had to try and, well, basically what it comes down to is that you don't know row. because you don't formally explicitly design it in your simulation. You don't construct it in your simulation. And so what you really have to do is that the best thing you can do is actually try to estimate rho in the actual simulation itself. And so if you want to try and recover that in the simulation, which is what we have to do to actually try and construct true alpha, you actually have to basically estimate it. So and so that's sort of one thing that I guess I should say that when I say true alpha, it is actually it's really an estimated true alpha, because we don't know the true alpha in the GE. We actually have to estimate it, and part of that involves trying to estimate rho from the marginal model.
You might guess my next question, and how about the dimensionality problem or the identifiability? If you're having effectively a rho which is the same size of the entire data set, how do you estimate that? Sorry, this buckles.
Yeah, that's a good question to ask. So the way we do it in the simulation, and we're not necessarily saying I'm not necessarily saying you do this in practice, because it's only because of the design of the simulation that we did this. Is that in the simulation, you to actually construct a true rho, what you can say is basically you kind of know, well, because in the simulation you know the true parameters, you can basically get a true A, basically a true Z, and then a true A, and then a true D, and then a true beta. And then based off that, you can then get an estimate of rho. And in that situation, actually, perhaps not surprisingly, the best estimate of rho actually turns out to be more or less a Pearson residual to actually construct the rho. So you actually can get an estimate of rho. Whether it's a good estimate of rho, that's an open question, and we've struggled with that because the problem is we don't know the true rho. In a Gaussian case, you can do this because in the Gaussian case there's an exact link between conditional and between the mixed model and the GE, so you can sort of at least do a check. But in a more general context, it's quite a bit harder to actually try and assess how good your estimate of rho is, because you don't actually know the true rho.
Thank you, Francis. It's very insightful. Thank you.
Thanks, Pauline.
Any other questions for Francis? Francis, I have one. I mean, I think you probably explained it, but I didn't quite get it. You know, you were saying the difference between restricted and non-restricted is that, or one of the drawbacks or possible drawbacks was that you were in fact interested in estimating the betas, but you're estimating the alphas. There is no way you can, if you estimate the alpha, back engineer what the beta is, because you have the beta and then you have plus some terms that are going to depend on the spatial location and on the covariance.
Yep, so very good question. So if I understand, basically, yeah. So, I mean, I guess the first comment I'll make to that is that there's a bigger issue of actually, and I think one of the points I want to make is the bigger issue is actually, are you interested in beta or are you interested in alpha? And I think that's a more general question, is that in practice, I'm not always convinced you're actually interested in beta. You may actually be interested in estimating alpha itself. And so on that respect, I think that's just something to keep in mind, and that does sort of one of my points regarding sort of why you maybe want to use restricted spatial GEs. But I guess your other point, which is really interesting that you raise, is basically you can sort of think about it as saying you could estimate the restricted spatial G and get alpha, and then basically try to reverse your way and then get back out to estimate the beta. You can do that, and we sort of thought about sort of at least maybe in a simulation or maybe in practice what happens if you try to do that. It's kind of to me it seems like it's an interesting thought exercise, but I didn't really understand sort of where this was trying to go, because I guess if you were trying to estimate beta in the first place, then you would probably use the unrestricted unrestricted spatial G to begin with, and then just go from that. So to me, I understand the sort of the kind of reversing engineering, trying to get beta out of alpha, but to me, it sort of felt like, well, I wasn't really sure what the practical benefit of doing that was. One thing I will mention, the final thing I mentioned regarding that particular question is that actually in the Hanks et al. 2015 paper, one of the things they in the context of spatial mixed models, and when you have random effects in play, the beta and the rho are both explicit. And so if you actually read the Hanks et al. Paper, they sort of at some point talk about doing this explicit reverse engineering. And the reason why they talk about that is that they're trying to sort of correct for standard errors in the Bayesian MCMC inference. So there is sort of a related point that occurs in the Bayesian context, at least in the Bayesian MCMC context. And I guess for me, maybe that it makes a little bit more sense in that context because you explicitly have beta and rho in play. So you can sort of interchange things, or you can muck around with things much more straightforwardly. Whereas in the GE, you have to try and guess the rho, or you have to try and estimate the rho. And so that's kind of why this reverse engineering, it wasn't as clear to me sort of why I wanted to do that. But there may be a reason, I'm just not really sure.
Yeah, I see your point. Yeah.
Thanks, Boris.
No worries. Any other final question for Francis or comment? Okay, well, if not, then we're going to thank you, Francis, again for giving a seminar. That was great. And it was recorded, so it will be put online on the blog very soon. Thanks, Francis.
Thanks, everyone.
I'll do the applause myself.